Hi guys. For those of you who don't know me, I'm Jay. I'm going to be doing a little bit of a binomial expansion review for you guys. I know you guys have the midterm one for 213 tomorrow, or maybe today if you're watching it late, or maybe yesterday. It'll also help you hopefully for the midterm two and the final. So let's just jump right into this. So, uh, straight up in the first week for lecture three, uh, our first activity for the day was this binomial expansion of 1 over quantity z minus r squared. So for part A, it says factor out the larger length to create a dimensionless binomial that is in the form of the binomial theorem 1 plus x to the n, right? And a binomial is just two things, a plus b, added together, right? And then if we raise it to some power n, right, that'll give us our ability to make it in like the binomial theorem and be able to use uh, what we have right here. So let's do part A real quick. So we have this 1 over z minus r squared term right here. And if we're going to be expanding this, we'll say, okay, let's check which one's much bigger. So it's r much, much less than z. So z is the larger item in here. And our binomial theorem right here, uh, 1 plus x to the n, is used if x is much, much smaller than 1. So if we say divide r by z, then it'll be much, much smaller than 1 and it'll satisfy this condition. So let's say, okay, we can rewrite this as z minus r to the power minus 2, right? Because it's a reciprocal, and so we can just negate this right here. For example, 1 over a to the n equals a to the minus n. So that's where that's coming from. And so using this z minus r to the minus 2, we can also expand it to say, okay, well, let's multiply by a special form of 1, or z over z, right? Because z over z equals 1, times z minus r, right? And we're dividing by z because that gives us a smaller quantity of r over z, because r is much, much less than z. So a small number divided by a much larger number is a much smaller number, right? And this is to the minus 2. So if I take this over z and bring it into this z minus r, we have, okay, z times, well, z over z is 1, 1 minus r over z, right? And this whole thing is to the power of negative 2. Now, if we have two things, a times b, and they're raised to the power n, right? That's just ab times ab n times, right? And so you can just say that this is equal to a to the n, b to the n. This will extend to our concept of negative exponents, and so we can say that this is going to be z to the minus 2 times 1 minus r over z to the minus 2. Now this has the form right here of 1 plus something very small to an exponent, which is our binomial theorem. And so let's make this, okay, z to the minus 2 times, well, we have 1, and then we have this plus this minus 2 times minus r over z, right? And that gets rid of this exponent right here. And now we've brought down the negative 2. And so we can simplify this to say it's 1 over z squared not equals. 1 over z squared times 1, negative negative cancels, plus 2r over z, right? And you can keep it like that after you've expanded it, or you can just uh, multiply it out, and that would be 1 over z squared plus 2r over z cubed, right? And we can work with these pretty well right here using these values from our question statement. Z equals 1.0 meters, and we have r equals 0.01 meters, right? Or 10 to the minus 2 meters, right? 1.0, sorry, 1.0 for sig figs times 10 to the minus 2 meters, right? So if we have 1 over z squared here, z is 1, right? And so this will be equal to 1 divided by 1.0 squared meters squared, right? Because we have that 1 over meter squared now that is in the denominator, plus 2r, 2 times 10 to the minus 2 over here, over 1.0, right, cubed. And the meters will cancel here with 1 factor of the meters cubed here. And that'll give this 1.0 per area plus this 2 times 10 to the minus 2, or 2.0 for the sig figs, times 10 to the minus 2 per meter squared. And so that'll equal about 1.02 per meter squared. Bring those units back, right? Notice how we factored out any units here. This little box, what I'm boxing right there in this, is unitless, right? 1 is a unitless number, and then we have meters divided by meters, which is also unitless, right? And so it was perfectly valid to perform this binomial theorem on it. Now, let's go to the second part, right? In lecture 5, on the fourth slide, we have this electric field at a far distance. So let's copy this down here and ask this question. What happens when we're going to do our binomial expansion on this, right? So this looks really complicated. We have a vector thing here equals a vector thing here. And to make this the best we can, let's just ignore this, only solely look at this part. And so now that I've written this out, right, and we know that x is going to be much, much larger than the distance d, well, what we're going to do, like we did the last time, is we're going to factor out the thing that is larger, which is the x squared, right? And so let's take this, right, this 2x, right, and I'm going to factor this x squared out times 1 plus d squared over x squared. And this is all to the 3 halves minus 1 over x squared, right? And then once we've distributed this 3 halves onto here, onto this x squared, right, we'll see something that looks very nice happen. And it's that we get 2x in the numerator again, and this is x. Now 2 times 3 halves is 3, so x cubed times 1 plus d squared over x squared, right? And that's to the 3 halves as well. And we have this minus 1 over x squared. But if you notice, we have an x right here, and that'll cancel with 1 factor to go to 2. And so we can actually just pull out a 1 over x squared and say, okay, 1 over x squared times this 2 times 1 plus d squared over x squared, right, to the minus 3 halves now, minus 1, right? And notice now that this is already in the form right here of 1 plus something very small to the power n. Um, and so if we use our binomial theorem on this, we'll rewrite this factor out front. 2 times 1 minus 3 halves times d squared over x squared minus 1. Now we have this 3 halves d squared x squared, and what we just showed in our previous problem is that something squared is actually really, really tiny. It barely affects it, and so we're going to actually get rid of this term, right? We're just going to say, oh, it's about 0, right? And I'm sure for all intents and purposes, it is functionally 0. And so let's say, okay, 1 over x squared, and now we have 2 times 1 minus 1, right? And that'll be, 2 minus 1 is 1. It'll just be 1 over x squared is the binomial expansion of this whole thing, right? Which is amazing because this is such a complicated formula, and then using this binomial theorem, we reduce it down to something that's a lot more usable, right? It's a lot easier to isolate for x when we have 1 over x squared than when we have this beast of 2x over this whole quantity to the 3 halves. That's a lot harder to isolate for x. I'm not even sure if it's possible to do, right? So instead, we can break it all down to that. And what that tells us about this situation physically is that the further away we get here, the less distinguishable these charges are from each other, right? This positive charge right here and here, right? When you're far away, this one, and this one right here, and this negative charge, they functionally just all add up. And we have 1, uh, plus 1, plus 1, minus 1. That'll be just plus 1, which is what we had right over here, over x squared. So we notice that as r is much more, sorry, not r, x is much, much greater than d, that this reality really shows up to us, right? But let's get on with this. It's more of a math video than this is a physics video right now. So knowing that, keeping that knowledge in mind, um, you can pause the video right now if you want to just think about it for yourself, but I'm going to tell you what the answer to this question is right now. So thinking about this thoroughly, we have a plus 1, right? A plus 2, and another plus 1. If we added those up in our heads, we know that it would be 4, right? So if we have 4 charges when we're really, really far away, it's just going to look like it's one big charge filled with 4 plus q, right? And the thing that represents this the best, we know that with one charge, we'd get this 1 over 4 pi epsilon naught term that we always get, q over r squared. But because we have 4 of them, right, we're going to expect a 4 right up here. And that is our answer right here. So the answer is going to be C. On homework 1, part D, we have this expression for the force of this dipole, specifically bisecting, right? But I'm just here to look at the math for this, and you guys have done the homework. So I'm just going to go ahead and do this for us. We have it rewritten out, and I'm going to put this into a form that we might like to work with it better. So we have that r minus s over 2, right, to the minus 2 minus r plus s over 2 to the minus 2. There's a lot of minuses in this one. This one's pretty tricky. I ask you to try this one yourselves. You've done it for your homework, but you might have forgotten it. So please go ahead and do it yourself if you have the time. So let's do that, the thing that we've always done. I'm just going to look at this first term here because it looks functionally identical for the second one. And so we'll just substitute it in later. So we have this r minus s over 2 to the minus 2, right? And if we know that r is much, much greater than s, right, given in the problem statement, r much, much greater than s, then we know that, okay, let's take out that r, and now we have this 1 minus s over 2r, right? And that's all the minus 2. Distributing the exponent, we have r to the minus 2, or I'm just going to rewrite that as 1 over r squared, and then times this 1 minus s over 2r to this minus 2, right? Now we can use our binomial expansion, right? We can just bring this down here. The minus 2's cancel with each other, and so that'll just give our 1 over r squared out front times 1 plus s over r, right? And notice that the only difference between this term, right, this term, and this term is that we have a minus sign here and a plus sign there. And so our other term should look like 1 over r squared times 1 minus s over r. And so we also get that these two added together, right, we can factor out that 1 over r squared. Then we have that 1 plus s over r, right? And remember, we're subtracting off this second term. So we're going to subtract off this 1 minus s over r. And if you do your algebra neatly and nicely, you get this 1 over r squared times this 1, and this becomes a negative 1, right? Cancel. And then we have this minus a minus, which makes it a plus, right? So we get this 2s over r, right? And then that'll give us 2s over r cubed. And then we can substitute that back into our expression all the way up here. Instead of that whole bracketed portion, and 2s over r cubed is a lot easier to work with, yet again, than that sum or difference of 1 over something squared. So yet again, it'll be a lot easier to work with, a lot easier to extrapolate data, and that's why we make these estimations. So let's go on to the next one. On homework 2, part C, we see that the net force is given by this equation, right? And if we want to do a binomial approximation, just like the rest of them, right, we have to notice that, oh, okay, we're looking at the case where r is much, much greater than z, right? Now, this was different than most of the other ones because the coordinate was usually much, much larger. In this case, we're saying that the coordinate where we're measuring is much, much smaller than some property of the system, right? The one further up, right here, this came from a plus and a minus. I'm not sure if it's in that orientation specifically. And we have a distance s between them, and we're going really far out, right? Really far out distance r. Whereas with this one, this comes from a ring, right? And we have some distance z away, and the radius of this thing is r, right? That's where this force equation is coming from this integrated charge loop. And so if we're really close to the center of it, right, we're going to be really small. So we're going to get some good approximations for this with this binomial theorem, right? So yet again, let's ignore this whole part that's attached to it, right? Because none of these are variables that we need to consider right now. We're just multiplying by them, and our other part is going to be separate to that. So let me write that out for us. And now that we have z over r squared plus z squared quantity to the 3 halves, right? Let's do what we've just done a couple times and factor out the larger part, this r, right? In this case is r squared and z squared. And if something larger squared is going to be much larger, and then something smaller squared is going to be smaller, right? So let's factor out this r squared, right? Squared 1 plus z squared over r squared. And that's all to the 3 halves. right? Bringing down that 3 halves onto each of these terms gives us, the z over r cubed term, right? Times this 1 over 1 plus z squared over r squared to the 3 halves. And that'll be equal to z over r times 1 plus z squared over r squared to the minus 3 halves, right? And before we even do this, let's recognize that this is also z over r, right? That's a small number, like we just discussed. Because if we divide r over, we'll get 1 is much, much greater than z divided by r, and a number much, much smaller than 1 squared is going to be functionally useless. So we can just say that, oops, I forgot this cubed on this. We can just say that that is z over r cubed times 1, or just, z over r cubed. So we have this one last thing right here from lecture 6, right? It's in the 12th page of the slides. And so let's do this last one real quick, right? This one isn't exactly a binomial theorem, but it is going to be useful. So when we get really, really far away, when z is much, much greater than r, right? What do we expect? So as r increases more and more, we would expect that this entire term would just go to 0 because r squared in the denominator is growing, taking the square root, so it functionally grows as r grows. So any number divided by an ever-growing number should just end up being 0, right? So we have this 1 minus 0, and so we just honestly get eta over 2 epsilon naught, right? Obviously, we have this z hat term that we should take care of, and then notice that it is away from the plate no matter what. That should be all I've had for you today. I hope this helps out some of you. I know I've talked for a while here. I'm going to grab myself some water. Uh, and I hope you guys all do good. I hope to see you guys tomorrow at my midterm review session. And I really hope that this helps. So I'll see you guys tomorrow. Bye bye.